Pre-calculus 5.3, day 1, solving trig equations. So solving these are going to involve using the unit circle values and being able to know where is sine of theta 1/2, where is sine of theta √3/2, where is tangent 1 or -1, etc., etc. And so we're going to have trig equations, so equations, things with equal signs in them, and you are going to use standard algebra techniques, such as collecting terms and factoring. And one of your goals is going to isolate the trig function on one side of the equation. And then we're going to keep going and solving from there. So there's just a combination of all these. So here we have an equation, 2 sine of x equals 1. I want to isolate the trig function, which is your sine x. So to do that, I would divide both sides by 2, and the 2's cancel, and I get sine x equals 1/2, which you see right here. So now I need to figure out the angles whose sine is 1/2, because I need to figure out what angle do I put in for x. And that goes back to knowing your unit circle and figuring out, okay, well, pi 6 reference angle, 30 degrees, has an ordered pair √3/2 up 1/2. And so at pi 6, sine is 1/2, but also at 5 pi 6, where we have the ordered pair -√3/2 and up 1/2 on the unit circle. There's another place where sine is going to be positive. Sine's positive in quadrants 1 and 2. Now, granted, there's in quadrant 3, we go to the left √3/2, but then we get a -1/2. And I'm not interested where sine is -1/2, so that's not important. Another way to look at this is graphically, because these are just solutions. So x equaling pi 6 or 5 pi 6 only involve angles between 0 and 2 pi. Well, we didn't restrict the domain, so anytime I do a full rotation or go to the next period, I'm going to get another place where the sine's 1/2. And this is demonstrated in the graph. So here we have a graph, and if I look at just the intervals 0 to 2 pi, which would mean from here and then 2 pi is here, just within that first rotation of a full circle, 0 to 2 pi, I have 2 places where the height of the sine graph is at 1/2, because this right here is at 1/2. And this x value, as they're showing you right here, is when x is pi 6. And this x value right here, as they're showing you, is when x is 5 pi 6. So sine in quadrant 1 at pi 6 is 1/2. Sine in quadrant 2 at 5 pi 6 is 1/2. But then sine goes below all the way from pi to 2 pi, and sine's negative, so I'm not going to have any place where the sine has an output of 1/2 from pi to 2 pi. And that has to deal with this whole thing up here that in quadrants 3 and 4, sine would be negative, and I'm not interested where sine's negative 1/2. I only want where it's positive 1/2, which is just your for quadrant 1 and quadrant 2. However, if I keep on going, or on a unit circle, here's that pi 6. Well, what if I rotate all the way, around another time? Well, that's taking that angle of pi 6 and adding 2 pi to it. That is going to be an angle that's coterminal, and that's another angle whose sine will be 1/2. But if I did that, I could have also just kept on going and done another full rotation, or had pi 6 plus 4 pi, or gone another one and had pi 6 plus 6 pi. And it just keeps on going and going. Every time I add another full rotation to pi 6, I end up with a coterminal angle, and the sine of that is going to be 1/2. So graphically, we can see this. They kept on going to the right. You have 2 pi, and then 2.5 pi, and then here's 3 pi. And if I keep on going to 4 pi, well, this graph is going to hit -1 at 3.5 pi and then be back at 0 at 4 pi. So right in here, that's a second period of sine from 2 pi to 4 pi, and it hits 1/2 here and here, which is that pi 6 plus 2 pi and 5 pi 6 plus 2 pi. And then we could, do that again, and we have another place here, and this is going to be x equals pi 6 plus an additional rotation of 2 pi, so add 2 pi to 2 pi is 4 pi, and this one's going to be when x is 5 pi 6 plus 4 pi. And we can do that for 6 pi, 8 pi, 10 pi, 12 pi, etc., etc. Well, not only can I keep on hitting 1/2 with sine as I go to the right, I can do that as I go to the left. So think about being at pi 6 and then rotating backwards. So you have a pi 6 minus a full rotation. You will be coterminal. And so we have that right here. Well, the same thing happens with the 5 pi 6. And I could keep on going back with sine, and I could hit a couple more places, which would be pi 6 minus 4 pi and 5 pi 6 minus 4 pi. And then I could subtract another 2 pi and be at minus 6 pi. So I have an infinite number of angles where sine of x is going to be 1/2. But the key to get started is what are the angles from 0 to 2 pi where sine's 1/2, which are these two, pi 6 and 5 pi 6. And then for each of those, if I add full rotations, which are multiples of 2 pi, I'm going to have another solution. So that's what I have right here. And they do this to write it concisely. We can't just say x can be pi 6, and then I have pi 6 plus 2 pi, and then pi 6 plus 4 pi, and pi 6 plus 6 pi, or go backwards, pi 6 minus 2 pi, pi 6 minus 4 pi, but it keeps on going in both directions. So how can I describe this in a way that indicates how it's changing? And how I do it is I multiply 2 pi by n, where n is an integer. So if n is 1, I get pi 6 plus 2 pi. If n is 2, I get pi 6 plus 4 pi. If n is 3, I get pi 6 plus 6 pi. By writing it that way, I can write all of these in one expression. And then I just need to state where n is an integer. And that includes going to the left because n can be -1, which creates pi 6 minus 2 pi, or n can be -2, which creates pi 6 minus 4 pi. Well, I need to do that not only with the pi 6, I need to do that with the 5 pi 6 as well. All right, so this figure below illustrates another way to show that this has infinitely many solutions, which I've already alluded to. And it's just the idea that if you're at pi 6, and then if I do a full rotation, that's pi 6 plus 2 pi. If I add on another rotation, that's pi 6 plus 4 pi, and et cetera, et cetera. So any multiple of 2 pi, if I add it to pi 6, I'm going to get a sine of 1/2. And the same thing with 5 pi 6. So very quickly, if I did cosine of x is 1/2. Well, cosine deals with x, and cosine's positive at pi thirds reference angle. It's 1/2 and up root 3 over 2. And it's also positive in quadrant 4 where on the unit circle we're to the right 1/2 and down root 3 over 2 with a reference angle of pi thirds. So this is where x is pi thirds. I'm going to leave room for the multiple angles, or 5 pi thirds. So you have to know within the unit circle, where is cosine going to be 1/2? And then to that, you would just add 2n pi plus 2n pi, and you would state where n is an integer. And that would be your solution to that. So again, knowing your unit circle values will be key to helping you make this go a little bit smoother. All right, so one of the sets of problems is just verify solutions. They want you to verify that this x equaling 3 is a solution to this. So what you need to do is realize tangent squared of x is tangent of that angle, and then you are squaring it minus 3, and we're going to show that comes out to 0. Well, pi thirds, we just saw, is 1/2 comma root 3 over 2, and tangent of pi thirds is your y over your x, which is root 3. So you need to show that you plug in root 3 into that, and then you get 3 minus 3 is 0, you get 0 equals 0, and you verified that it's a solution. Then it says verify 4 pi thirds. Well, again, tangent of 4 pi thirds, and you're going to square it, minus 3 equals 0. Well, 4 pi thirds is going to have a pi thirds reference angle, quadrant 3. It's pi plus an additional pi thirds. That's to the left 1/2 and down root 3 over 2. And so the tangent of 4 pi thirds is the y over x. It's that negative root 3 over 2 over negative 1/2. Negative divided by negative is positive, and again, you get root 3. So you get root 3 squared minus 3 equals 0. 3 minus 3 equals 0, so 0 equals 0. And it checks, it works. So you need to show detailed work on that to see that they come out and they satisfy that equation. All right, so now let's get to solving some trig equations. And one thing is, we mentioned, is collecting like terms. And then after that, we're going to isolate the trig expression. Well, I'm going to go ahead and add cosine x to both sides because those are like terms. And so I get a 2 cosine x minus root 3. And don't forget the equals 0. That's pretty important. Work down the page. Start by writing the original problem. Then isolating cosine x, add 3 to the other side. And then divide by 2. So now, what angle has a cosine of root 3 over 2? And so what I'm thinking is cosine deals with x, so that's quadrants 1 and 4. And it's root 3 over 2 at pi 6. Because on the unit circle, the x-coordinate at pi 6 is root 3 over 2. And that's true also in quadrant 4, that we get a positive root 3 over 2, but down 1/2. So the angle of pi 6, or the angle of 11 pi 6, is where cosine's root 3 over 2. So we are going to write root 3 over 2, but then every full rotation, you're going to get an angle coterminal with it. So root 3 over 2 plus 2n pi. And then x equals 5. Oh, I just wrote root 3 over 2. I'm so sorry. Pi 6, the angle, plus 2n pi. And then for the second one, I'm going to erase this. Second one, we are in quadrant 4, and that's 11 pi 6. 1 pi 6 short of a full rotation, plus 2 n pi. And on both of this is where n is an integer. Well, there's a faster way of writing where n is an integer. And what we do is, this reads n, it's kind of a scripted E, is an element of the integers. So this right here reads n is an element of. That is an element of is that kind of scripted E. And z is a set of integers. So we can just write and be a lot faster than having to write out where n is an integer. And then these are your solutions. And again, the 2n pi is just because cosine keeps on going to the right and left when you graph it. It's going to hit this root 3 over 2 an infinite number of times. And that's how we can write those answers concisely. All right, so solving algebraically. And this is going to involve square roots. You need to isolate the trig function. And so I'm going to write the original down, and then I am going to add the 1 to both sides, then divide by 2. But then I need to take the square root. And when I take the square root, I need plus or minus the square root of 1/2. And that's plus or minus 1 over root 2, but you need to rationalize. And you get plus or minus root 2 over 2. So I'm looking for the angles where cosine is either positive or negative root 2 over 2. And I know those are angles that will have pi 4th reference angles, or 45 degrees. And so on this one, I know in quadrant 1, in quadrant 2, in quadrant 3, and in quadrant 4, at all those places where we have pi 4th reference angles, here would be root 2 over 2 up root 2 over 2. Here would be negative root 2 over 2 up root 2 over 2. Here again it would be negative root 2 over 2 down negative root 2 over 2. And here would be at positive root 2 over 2 down negative root 2 over 2. But at all of these spots, the x coordinate is either positive root 2 over 2 or negative root 2 over 2. Now, so I can go, whoops, x is pi 4ths plus 2 n pi, or x is 3 pi 4ths. That's where it's negative root 2 over 2 plus 2 n pi, or x is 5 pi 4ths plus 2 n pi, or x is 7 pi 4ths plus 2 n pi. And that's not incorrect, but there's something new about this problem. And what's new about this is that between each of these, in terms of rotations, so if I go from here to here, it's a 45 or a 90-degree rotation. If I go from here to here, it's a 90-degree rotation. If I go from here to here, it's a 90-degree. From here to here, it's a 90. Every one of those has the same amount of rotation between those. So I can actually write this more concisely as pi 4ths, and then I want 90-degree rotations between them, so I can make it pi halves times n. where n is an element of the integers, and I can write it more concisely. And so you can write them like this, but it's not the best answer. It doesn't show the best knowledge of what's happening. So this is the better way to write it. But I get that's getting a little bit advanced, but I'm sure many of you can figure that out and understand that. Don't forget that n is an element of the integer. All right, so another thing that we mentioned is factoring. So I have a cosine squared and a cosine x. And so what you need to do on this one is move everything to the same side. Do not divide by cosine x, you will lose solutions. Do not divide by cosine x, you will lose solutions. Move everything to one side, set it equal to 0, and then I can factor out a cosine x. So it's a little bit like 2x squared equals x. You should move the x to the other side, set equal to 0, and factor out an x. Only it's not x, it's cosine x. But that's the process. You shouldn't divide by x here. You'll lose where x is 0 as a solution. I cannot emphasize that enough. So with that, we are going to continue. We have a zero product principle. If I have two things multiplying to be 0, either A is 0 or B has to be 0 for that to be true. So we're going to do the same thing here. Either cosine x has to be 0 or 2 cosine x minus 1 has to be 0. And the second one you need to keep solving. Add 1 to the other side, isolate that trig function, and we want to know where cosine of x is 1/2. So on this first one, cosine of x being 0. Same thing happens with sine of x. There's kind of a unique thing that happens. We can think about the unit circle, where cosine 0 is one of those axial intercepts. And it's where x is 0. This is the point 1, 0, so it's not there, but here at 90 and at 270, or at pi halves and 3 pi halves, you get the x coordinate to be 0. At pi, it's negative 1, 0, that's where cosine's negative 1. But both here and here on the unit circle, the x coordinates are 0, so I have two places where cosine is 0. And kind of like what I said before, notice that if I go from one to the other, there's a rotation of pi, half of a turn. So there's going to be a more concise way of writing this. Also, if I think about it graphically, cosine starts at 1, goes to 0 at pi halves, negative 1, 0, and then back up here. So if I have this cosine graph, I go back here. Every time it hits 0, there's a distance between them. This distance is pi. This distance is pi. That's that same idea that I'm trying to show up here. So cosine hits 0 starting at this value, which is pi halves, and then every pi units thereafter. So the answer for this is pi halves plus n pi, not 2n pi, because it's just 1/2 of a term, where n is an element of the integers. So that's the best way to write that. Now, it is true. You could say it's x is pi halves plus 2n pi, or x is 3 pi halves plus 2n pi. And again, where n is an element of the integers. But this is your better answer because it shows a better understanding. But that's just for the first part. So then we have 2 cosine x minus 1 equals 0, or where is cosine of x 1/2? Well, cosine's 1/2, it's going to be positive in quadrant 1 and in quadrant 4. And I had kind of gone through this one earlier. When it's pi thirds, this is to the right 1/2 and up root 3 over 2. Or in the fourth quadrant, it's to the right 1/2 and down negative root 3 over 2. And on this one, the distance between is not the same, so I have to write them separately. And so this is where x is pi thirds plus 2n pi, or x is 5 pi thirds plus 2n pi. And again, where n is an element of the integers. So your answers to this is the best answer for the first one, and then there you have that. All right, and so that example 4 was one way to factor, but then we have quadratic in nature, example 5. And so the first thing, I've got a sine squared, a sine, and a constant. I'm going to move it all and set it equal to 0. And then I'm going to factor this. It's that 2s squared plus 3s plus 1. If you do this, please do this off to the side. So how is that going to factor? A 2s and an s. And with positive 1 and a positive in the middle, it's just got to be plus 1. And that would get me that middle term of 3s. So the s is sine, so this is going to factor 2 sine x. This is going to be sine x. And to get a positive 1 at the end and a positive middle term, they're both plus 1. And then we have the zero product principle. We have two things being multiplied to be 0. Either a is 0 or b is 0. So we have 2 sine of x plus 1 equaling 0, or sine of x equaling negative 1. So on the first one, you need to solve for sine of x, isolate it, and you get sine of x is negative 1/2. And for that one, I need to recall that sine is going to be negative 1/2 with a reference angle of pi 6 in quadrant 3, and with a reference angle of pi 6 in quadrant 4. This is where I'm going to have negative root 3 over 2 down 1/2, or positive root 3 over 2 down 1/2 on the unit circle. And since those y values are negative 1/2, those are angles where the sine is negative 1/2. So x is from here to here, reference angle of pi 6 is 7 pi 6. And then all the way to here, with a reference angle of pi 6, is going to be 11 pi 6. And then you need the plus 2n pi plus 2n pi. And again, n an element of the integer. So that's good for where sine is negative 1/2. Now for where sine of x equals negative 1, I can think about the unit circle, but that's an axial intercept. And it's where on the unit circle, the y-coordinate is negative 1. And that is right here, which is 3 pi halves, or 270 degrees. I can also think about just for one period of sine, where this is 2 pi, this is pi, this is your pi halves, and where it hits negative 1 is that 3 pi halves. So I could think about it graphically to figure out, oh, well, sine will hit negative 1 only once during its period, and it's at 3 pi halves. So for this part of the solution, it is 3 pi halves and every full rotation, so plus 2n pi, where n is an element of the integers. And so both of those are needed for that solution. So you have some algebra techniques, and plus you need to make it go smoother, you need to be good with your unit circle values, and this is an opportunity to practice those. Don't take shortcuts. You need to know these.